Yep, we're live, and I'll switch focus. Easy. Welcome. Okay. Alrighty. Welcome everyone. Thank you for coming along to our beginners security workshop. If you haven't yet, please just take a moment to fill out the attendance so we can get that $2 per person and spend it on, I don't know, yeah, something like that, yeah. But yeah, please take a moment to fill that out. And with that, welcome to our introduction to cybercrime. Now before we start, I just want to give credit because a lot of these slides were inherited from last year's education team who did an amazing job. So big love to them. I'm not exactly sure who made these slides, but it was definitely one of them. So big respect. But what are we going to be talking about today? So welcome to your life of cybercrime. Throughout today's 2 hours, we're going to turn you all into hardened cyber criminals capable of wreaking havoc wherever you go. We're going to be learning a bunch of techniques, a bunch of the different areas that come with like information security and the sort of information security mindset that we like to practice in the cybersecurity industry. So for a moment, I'd like you to imagine that you are a criminal. And looking around this room, I kind of feel like some of you may not need to imagine, but either way, imagine you're a criminal. At least I hope you're right, yeah. Your task is to break into a house. All right, I want you to try and brainstorm 10 different ways you could gain access to someone's house. Don't share your answers just yet, just maybe write them down, and then we'll go around the room and maybe pick out each person's best or most creative answer. So I'll give you about 3 minutes to think of different ways you might be able to break into a house. Hello. It's easy, you just throw it to them and then actually just come on the recording. Yeah? Fair enough.
Break upstairs, break downstairs, break up and downstairs. There's only one floor. Break remaining with
All right, I might bring it back in. So the great thing about this exercise is that whoever starts first has the easiest time coming up with ideas. So I'll think about where we want to start it. All right, we'll start over here.
We're going to pretend we're the police and then trick them.
Okay.
Yeah.
So pretend to be like a source of authority and then get in that way. I like that idea. Does anyone else have one, like an idea they're especially proud of? Otherwise I'll throw it around the room. All right, we'll go to the person next to you.
Break down the
Yeah.
just break through the windows.
That makes sense. Brute force, I like it. How about you?
Jumping over like the backyard fence, going into the backyard.
Yeah, it's a good idea. Somewhere where the security is like less intense, right? Yeah, that makes sense. Maybe over here?
Set the house on fire.
That makes a lot of
They'll
sense.
run out and unlock the door.
So if you can't have access to their home, then nobody can, basically. Okay.
You do get access because they run out, unlock the door.
Ah, okay, I like that,
You don't have very
yeah.
long, but
That makes a lot of sense, actually, yeah. Okay, creating a sense of crisis, I guess. Yeah. How about behind?
You could just try and like open the door anyway, see if it's like unlocked.
Okay, yeah, just checking each, like maybe windows as well to see if there's any unlocked like that, yeah. And maybe in front?
I just say find the spare key if they have a spare key in the front door.
Yeah, that's good thinking as well. A lot of people leave a spare key around for that sort of scenario. How about you over there?
Maybe get the house owner to invite you in as a friend or something.
Ah, it's like the long con, right? Slowly befriend them,
Long game, yes.
and then have them invite you over, and then it's not malicious. That's a good idea. You over there?
See if you can open up the garage door using like a customizable remote.
Yeah, okay, I like that. Maybe over there?
Pretend to be Santa and go for the chimney.
Definite good use of social engineering there. I like that. And you there?
I feel like everything's been said. I would dig a hole underground.
Okay.
Out from underneath.
Like the Great Escape kind of thing.
Exactly.
Yeah. You can do the thing where you like put the sand in your pants and like slowly, yeah, okay, that makes sense. And behind?
All of my ideas have already been said, to be honest.
Fair enough. Yeah, it gets harder and harder as it goes on because all the good ones get taken, I guess. Maybe behind you?
I'd probably put them to leave and just go in my door.
Fair enough, like knock down the door kind of thing. Hey, oh,
Cybersecurity.
absolutely.
Let's see faces now.
Yeah?
I don't recognize anybody yet. So.
I don't know if anyone said this. Locksmith. Like you just try to unlock the door with just some tools that locksmiths use.
Yeah, just try and pick the lock kind of thing. That makes a lot of sense. Very much in the spirit of SecSoc as well. How about you two over there?
Knock the door and ask them to let you in.
Yeah?
That's a bit like plumbers. Like when you fix the
Yeah.
tap.
Okay, I like that, yeah. You could do something like, I don't know, what kind of person would a person like let into their home? I know we said like police officers, but I wonder what other people would have that kind of authority that would just be let in, no questions asked. All right, cool. I think we've kind of gotten around to everyone, unless anyone else on this table has any particular ideas.
Did anyone just say like after we let in?
Yeah.
Alright.
Nice. All right. Yeah, those are all good ideas, and they kind of exemplify the fact that, like in security, there's a lot of different ways to approach these kind of problems, and there's like, even with just a simple house, there's so many different ways you can kind of go at trying to gain access and get in. So why did we do that? So people often think security looks like this. Not that image specifically, I'm assuming, but kind of in the sense that security is kind of securing everything, right? You've got a broad perimeter, and it's kind of, everything's secured behind some fence or some firewall or some sort of ultra secure thing that you've got to kind of find a really clever and neat way to get around. So maybe in the case of this fence, right, maybe you've got to pick the lock or scale the fence or do something, James Bond-esque like that. But in reality, security, more often than not, tends to look like this. Particularly in the case of information security, because the internet's just so huge and the services on the internet are so varied that realistically, sure, a lot of services or a lot of things are going to be secured, with this kind of good security, but more often than not, somewhere else, there's just a giant gaping hole like we've got there, where you can just walk in, essentially. So that's kind of how we like to think about security, or part of how we like to think about security, particularly information space. We like to think that there's always some way in that requires significantly less effort than you would have first imagined. So what are we going to be covering today? So today we're just going to do a pretty broad overview of a lot of what we think are kind of the core concepts in security, or in information security. So we've got forensics, cryptography, binary exploitation, the web, and then just some upcoming content that we've got coming this year. So, our intro, the security mindset. So the goals for this workshop, we just want to show you what security actually is, try a variety of different security topics, warm up for more in-depth workshops that we've got coming later on, and possibly gain a few skills that might help with solving CTF challenges later in the term. A couple of admin things. SecSoc is a firm participant of the Do Not Get Arrested Challenge 2023, as in all years. I personally have a 21-year streak, and I'm not looking to lose it. So, as fun as hacking will be, we still need to follow the law and make sure we don't access or interfere with computer systems that we don't own or have permission to access, physical property that doesn't belong to us, as tempting as it may be. Do not attempt to hack any real websites or your friends. Right, I think that absolves me of all legal ramifications if you do anything bad, which is good. There's also the good faith policy. So on top of following the law, we just want to make sure you're all being, kind of good people, I guess. So welcome. All good. So, along with following the letter of the law, we kind of expect you to, act in good faith at all times, be a good citizen, not invade, alter, or damage the other's property, invade the privacy of others, break any laws or regulations, annoy other people, deprive others of access to resources, or the last one, which is do or omit anything else, so on and so forth. So basically, even if maybe by the letter of the law it's technically legal, we kind of expect you to still use your better judgment and not be a bad person, basically. And this, the added bonus is this little kidney thing is also really happy when you do that. And happy kidneys mean a happy life, so we'll keep going with that. And with that, I'll hand it over to Lachlan to start with our first topic, which is forensics.
Cool, let's get into some forensics. Somebody shout out, what is forensics? Unfortunately, it's on the slide for us. In the security world, it revolves around analyzing and recovering materials in a digital device. You might have encountered it in forensic science or forensic other stuff, where you're just trying to search and find stuff. Let's try a simple example involving a photo. All right, if you know what this is, because it's kind of famous, don't shout it out. If you don't know what it is, try and shout out things you can find in the image, which will kind of lead us in the right direction to figuring out where the hell we are. There's a flag. Awesome. Any other ideas?
Building style.
Nice. There's some building styles. There's a costly looking thing in the background. Nice. Anything else?
Number plates, can you zoom in?
Yeah, cool. So we're somewhere in the UK. That's going to come into relevance later. But we can see these number plates. They're a bit blurred out, so we can't just search them up and try and find exactly where we are. So let's do some investigating. So we're going to Google Castle Flag UK, try and figure out where the hell we are. Does anyone notice anything interesting here? Yeah, that's literally just the picture we just saw. And it's Windsor Castle, which is really famous, and shame on you if you didn't know what it looked like. Photo from a Comp 6441 exam question. Where are we? Once again, if you actually know the answer, don't just shout it out. But can we see anything here that will help us? Westpac? Yeah, Westpac, easy. Some kind of police guy? Badge, yeah. So we can figure out the state pretty easily. Cool. So we've got a New South Wales police car. We can look at that police badge. Nice. There was also a road sign in the background. And what can we do with this road sign? Any ideas? It doesn't tell us a name. It just says RD. Any ideas what we can do with this? Google, reverse image search, both great ideas. So the point we want to get across as well is up to this point and for a little while longer. We need no actual technical knowledge, right? We just need Google. That's all we've been using, basic logic, Google, observation skills. So street signs are specific to local councils, the design, this kind of purple and yellow pattern is unique to a specific part of New South Wales. So we can maybe use that to try and figure out where we are. Something like this, which I literally just Googled, New South Wales council road signs, and I got this image from Reddit, because Reddit's amazing. So what do we see? Yeah, easy, Marrickville Road. And it turns out if we Google Westpac, Marrickville, we just like find what we're looking for anyway. But we can use this real estate sign in the background as well. That's another pathway to trying to figure out where we are, including Westpac, literally just Marrickville Westpac, and we basically find something which looks very similar to what we were looking for, which is really cool. We just needed Google, a bit of basic observation skills, and a little bit of time. Welcome to the world of open source intelligence. And this is like a fun challenge for you guys. This only requires like a bit of time and Google. Which company builds those things? As an added bonus, the way in which you find out which company supplies these things will also tell you like how these things function based on the spec on their website, which is pretty cool if you wanted to hypothetically like rickroll everybody at your train station. Moving on. There are some other tricks up our sleeves as well, which require a little bit more technical knowledge, you could say. Extra words we can't see. Any idea what we're talking about here? Shout it out if you want to be pretentious. Metadata. For example, data about a song, like in your iTunes library, if anyone still uses iTunes, it might tell you information about where it was recorded, who the artist is. That data is all in the file itself. Maybe data about an image. They can tell us the title, the author, the camera used, the location the image was taken, also the time the image was taken often. Metadata on your computer's file system normally has file creation date, modification date, other useful information the file system tags, like user comments maybe. And we can, in the previous example, we could have skipped all of that Googling, just chucked the image into something which can view metadata, and it shows us a bunch of interesting stuff. It was taken on an Apple iPhone, and we noticed this user comment, bank robbery, in which case, what are we going to do? Old mate Google, that's what we're going to do. Bank robbery, Westpac, and we find this. So it gets us to the solution, gets us back to the solution. The timestamps match from this person's Twitter, so we're like, nice, we found it. So how do we look at metadata? So you can use those online websites, like that was probably a screenshot from, or you can use command line tools like exif tool to read and write metadata, in which case you basically just download exif tool, type out in your command line exif tool and the name of the file you're looking for. And that will often come up in, for example, CTF challenges, which involve files, which involve images, etc. For an example of this kind of relevant in the wild, BTK, the famous serial killer, was on the run for more than 30 years. He came back to take another victim, sent a floppy disk to the police because he was an idiot, didn't clean the metadata, and they found him. So clean your metadata, guys. Let's look at a CTF challenge as well. First of all, what makes a PDF file a PDF file? What makes a PDF file a PDF file? Why is a PDF file not an MP3 file? Why can't we watch a PDF? Any ideas?
Because it doesn't follow the spec.
Sure. I mean, what is a file, right?
Is it allocate certain amount of memory?
Sure, it's just a bunch of data, right? Just a bunch of data. So in order for a PDF file to be a PDF file, there needs to be something special about that data, which is unique to PDF files. True? Right. That's perfectly logical. Now we've got a question here. If we renamed hello.pdf to hello.txt, is it still a PDF?
Yes.
Yeah, it is. And this kind of file extension idea is mostly just to help humans who can't read a bunch of raw data and be like, oh yes, this is a PDF. It's just like helpful semantics for us people. Computers often determine the file type by looking at the first few bytes of the content. It's like a header, if you're familiar with that idea. That's considered the file signature. There's an example. So what if we were to change the bytes to something random? We will corrupt the file. The computer won't know what type of file it is, let alone what's in the file. And your professor will be like, oh, looks like your data is corrupted. Can you please resend it? And then you just take a week to resend that file. So we're going to look at a CTF example in a minute of that. To look at the byte data of a file, if you open it up in like Word or whatever, it won't work, right? So we're going to need often a specialized hex editor, or even I think some basic text editors can still handle it. But it looks nice with this kind of hexadecimal format if we use a hex editor. And an example of that is hexedit online or hexedit through the terminal if you're cool. Let's look at an example. So we've got this file here which is delivered to us in the CTF called challenge.txt. We're told that it's a text document. Any ideas what we're going to do? We've got a text document here.
Open it up first.
Yeah, open it up just in like Notepad or something, right? So we're going to open it up in Notepad. It's a little bit fuzzy, but what it says at the top there is PNG. PNG, what's a PNG? Right, it's some kind of image file. It's a specific type of image file. So any ideas what we're going to do with this file?
Open it in the image viewer.
We could open it in an image viewer. Because we're on Windows, there's a little bit of a quirky thing that Windows doesn't like it if you try to open a TXT with an image viewer often. Right. We can rename the file to a .png and then try opening it in a thing. Now, if we were on Linux, we could also use this EXIF tool that we talked about before. That would also tell us it was a PNG. There's multiple ways to determine this information. Cool. So we're going to rename it a PNG. We're going to open it up in just like the most basic photo viewer. And we find out, yay, it was an image file all along, and we get the flag. Pretty simple? Yeah, nice. But let's go a little bit into more detail on this idea of image forensics. Because sometimes messages can be hidden in image files. And we call this steganography, the process of hiding information within other information. Image files are often really big, while text is only a few bytes. So it's kind of like hiding a needle in a haystack situation. You can get away with hiding text information in a huge image file and hiding it pretty damn well. So steganography. A really, really basic example of this would be if we just took a random image somewhere, then grabbed like the pen tool on Photoshop or whatever, changed the color, like RGB values by a tiny amount, and just like wrote in the corner like a message, right? That doesn't require very much technical knowledge, and to reverse that, you just zoom in on that part of the image and just like look at the slight color correction. But what's more common is using kind of more cryptographic style techniques. So we're going to talk a little bit about LSB. That is just a bunch of binary numbers. What that represents, though, are the RGB values. So if you've ever worked in kind of any image color stuff on your computer at all, you probably will have come across this idea of RGB values, where basically every pixel on a screen or even on the projector is being represented by a certain amount of red, a certain amount of green light, a certain amount of blue light, and those all get combined so your human eye sees that as a certain color. And we store that data as kind of 8 bits per color. And that's an example of, let's say, the R value. If anyone's good at mental math, they can just shout out what the decimal representation of that is. I'm basically trolling. Yeah. So from what we know about binary, though, if we change the final digit in that number, we're only going to do like a plus or minus 1, right? Because that value represents 1, the one all the way at the other end represents like 2 to the 8 or something. So that's going to change the value by a lot, but the one all the way over here is hardly going to change the color value, right? We could change like 173 to 172, and a human eye will look at the picture and barely notice a difference. The computer notices a difference because we've changed a bit. And in an image file, you don't just have like one R value. You've got a crazy amount of like RGB values to work with, especially in a big image file. And just by changing this least significant bit, we can barely change how the image looks, but we're able to hide a message inside it, a series of 1s and 0s. And that's kind of the fundamental idea for image forensics and steganography. And because that's, if you implement it specifically like that, you can find it pretty easily. So people are tricky and they create a bunch of programs to do it in more complicated ways. Often in a CTF though, it's going to be a pretty simple kind of stego technique. Or they're going to tell you, like, there's going to be metadata which tells you which program was originally used to encrypt and you can reverse it. Maybe they'll give you a copy of the original image and then you can do some analysis between the two images to figure out what went wrong, what changed. Cool. So this is just a tiny little taster because we're trying to give you like a little snippet of lots of different things. If this is something you're interested in, keep your eyes peeled because we might cover it more in future workshops. So with that, we're going to swap back over.
All right, so crypto. So what is crypto? Well, you know it, you love it. It's this thing. Now, I was told that this is like not fresh enough now, apparently. So I thought that like these like monkey dudes were kind of the in thing at the moment, but apparently I was talking to a friend who's into crypto and he said that this is like more accurate to how it really is these days. So, you know, you've got your crypto meme in there. What are we actually talking about? So we're talking about cryptography. So it refers to a method of storing and transmitting information so that only the intended audience can read and process it. So what does that mean? So basically, we want to be able to send information to another person and know that nobody in the middle can read or tamper with or in any way sort of mess with that information. So the general way it usually works is you've got your plain text, which is the information you want to send. You've got your sender. The sender does something to it, encrypts it using some sort of algorithm. You then get ciphertext, which gets sent to the receiver, who then does the opposite or however the decryption method works in order to get the same plain text that we had at the start. And the important fact about this ciphertext is that it can't be read by anyone in between. So why do we do this? Well, there's multiple reasons or there's multiple motivations behind wanting to encrypt things, and some of them are a little more obvious than others. So the first one's like kind of self-explanatory. Obviously, we want to be able to keep the contents of our messages secret, right? We don't want people to be able to read what we're sending to other people. But the other ones are a little bit less obvious. So we've also got authentication, right? We also want to find a way by which, like our messages, we can verify who they've come from. So we know that when we receive a message from a certain person and we decrypt it, we know that only that person could have, we know that only a person fulfilling a set of criteria could have sent it, basically. We also want integrity. So just because the contents of a message is secret or can't be decrypted doesn't mean it can't be tampered with in transit. So we want to have some sort of method for making sure our messages stay the same when they get to the receiver. Because theoretically, like a man in the middle can take an encrypted message, change it, and still pass it on to the receiver. And without some sort of integrity check, you know, that can have ramifications as well. And finally, we've got non-repudiation. So this is kind of similar to authentication and kind of not, but essentially we want to make sure that the sender, once they've sent the message, they can't feasibly deny having sent it, right? So say you've got, you know, two people sharing one encryption key, you know, one person can't encrypt a message and send it to themselves and then claim that the other person sent it to them. The message has to have come from that specific sender. So those are sort of the four main qualities we sort of aim for when we're doing encryption. So what's like a very basic example of encryption? Going right back to basics. So one of the earlier examples of encryption is the Caesar cipher. And you might have heard of it. It's pretty simple. Essentially, it's what we've got here. We've got this wheel, and on the outside we have like our alphabet of, I can't remember which, doesn't really matter. One's the plain text, one's like the resulting ciphertext. So say we want to translate a message like this one here. We'd take the first letter of our plain text message and then we'd swap it with the letter on the inside here. So basically you've got, you know, one alphabet kind of rotating inside the other. It's fairly simple, but you know, it sort of results in a message that is kind of confidential, I guess. Can anyone think of any issues with this method?
I guess it would be like pretty easy to break because all of the like letters are being moved by the same amount. So if someone had like a lot of time, they could just like move it 26 in each direction.
Yeah, exactly. That's pretty much, I mean, that's the main issue. Like, all you need to do is just shift that round 26 times, write out the message 26 times, which is, you know, not an unfeasible task at all. And you can easily figure out, you know, the original plain text message. Can anyone think of, maybe based off of kind of some of the qualities that we discussed before, maybe think of some like less, maybe some slightly tricky issues?
No way to authenticate, no
non-validation,
what are the points you
Textbook answer, I like it, yeah,
exactly.
Fair enough, yeah. Yeah, I guess those are also other issues as well. But yeah, the main issue is that, yeah, it's really easy to break, basically. But a slightly less obvious issue is also that, like, we can do it the brute force way, but there's sort of other ways we can break this encryption code. So in the English language, not all letters are made equal. Some of them we use a lot more frequently than others. So one way we can break this form of encryption is we can just analyze the number of times letters occur in the encrypted message and then kind of match them up with the number of times we'd expect to see letters occurring in the English language. So I think from memory, E is the most commonly used letter. So if you saw an encrypted message that had like one letter used very frequently, more frequently than any other, you could maybe replace that with E and then sort of do the same for the next most frequent letters. And there's a good chance you could probably decrypt, at least some of the message that way. Yeah, so basically, as I said, yeah, you can use that to decrypt it and then figure out whatever the alphabet shift was, basically. And then, yeah, as we said, easier yet, we could just test all 26 methods and see which one produces a proper plain text sentence, basically. All right, so here's a practice task for you, and whoever gets this first, I'm expecting you to shout it out really loudly. I mean, you've got to shout it with conviction as well. You've got to really mean it.
SecSoc delivered the best workshop.
Oh, thank you. So kind. Yes, exactly right. All right, so building on the Caesar cipher, we kind of want to get around this issue of being able to easily brute force our combinations, right? So another technique we can use is, a cipher that's similar, but instead of having like an alphabet inside another alphabet and only 26 possible combinations, instead we can just match up the letters randomly, basically. As you can see here, you've got your plaintext alphabet at the top and your encrypted alphabet at the bottom, and you can essentially lay out the encrypted alphabet however you want and match it up to whatever letters you want. And essentially you've got significantly more combinations of possible keys and codes that make it a lot harder to brute force, significantly less feasible to brute force, if that makes sense. So in this case, if we were to translate hello world by this cipher, you take the H, I can't remember where H is on the alphabet, up here, you translate it into the I, you take the E into the T, so on and so forth, until you get this encrypted message here. And it's, significantly more difficult to brute force. But it still has other issues. And we kind of touched on this with the last cipher. But can anyone think, without attempting to brute force every possible combination of this mess, can anyone think of ways that we might be able to more quickly decrypt something that's been encrypted with a cipher like this? Yep.
It's the same thing you said before, where you could look for the commonly occurring letters. Yeah,
exactly. Yeah, you can do sort of frequency analysis and figure it out. There also might be another way as well. Can anyone think of possibly another strategy you could use?
Brute force it and then check which ones have actual words in them, and then output those as ones to look at.
Strictly speaking, you could do that, although I would say that's probably a lot less feasible in this instance. But yeah, that's still a very valid strategy. But can anyone think of maybe another? Yes?
Question for the class.
Yeah.
How many potential combinations are there here?
I expect you to say the entire number, by the way.
The 26 factorial, 26 factorial. So that's a reasonably big number.
Yeah.
So 2 clicks of brute force.
Yeah. Yep.
I mean, you can do a combination of the frequency analysis for some words. So, for example, it would be pretty easy to get these.
Yeah.
In your thing, and you can keep on doing that until you've got enough of letters translated essentially for you to be able to start being able to guess at what the word could be.
Yeah, exactly. Yeah, that's another really good strategy that we can try and use. I think I've got an example here. So manually breaking a cipher like this, we've got the strategy of finding commonly occurring letters, that's a very valid one. And then we've also got this sort of second strategy we can use here as well. So there are certain features of the English language we know, there are only basically those one-letter words. So if we see a one-letter word having been encrypted with our substitution cipher, we know it's probably an I or an A. There are also not that many two-letter words, and a lot of two-letter words are used with varying degrees of frequency. Cool. So, you know, you've only got like this sort of selection here that we've got. And you can see here, like, there's a list of the most frequent, you know, words with particular frequencies. Like, you know, again, there's only 2 one-letter words. You've got the classic frequent 2-letter words and the 3-letter words, and it gets a little more complicated with the 4-letter words. But even then, like, you can kind of take context clues and you can kind of figure this stuff out. So we'll start with a little example here. So we've got a message that's been encrypted using a substitution cipher. So already we can see there's a 1-letter word there, and we're going to take just a gamble. And again, when you're actually doing this in real life, it's more a sort of a game of sort of trial and error. Like, you'll try a few things, realize it doesn't lead to anything, try another few things, so on and so forth. But for the purposes of this, we'll take a gamble, and we'll say that this 1-letter word is probably A. So just by doing that, we've already revealed like one of the letters in another one of the words. If we continue on, we can see that we've got like two-letter words down here, and we can see that they both start with the same character. Now, generally speaking, I guess intuitively, I tend to assume that I tends to be a letter with which 2-letter words frequently start. So I'm going to take another sort of guess here and say that maybe the first letter of these 2-letter words is I. And then you can start getting into context clues. So, all right, what are some common 2-letter words that start with I? You've got like is and it, right? And I'm not sure I can think of any others. So you kind of look at the sentence. You think, okay, is this one is or is this one it? Well, if this said is it, you would kind of expect there to be a question mark on the end, right? So it's more likely in this case, since it's a statement, to be it is. So we can kind of fill in those 2 characters there. And then as we do that, we can kind of see the words starting to take shape, and you can kind of see, like, you know, where characters might go. You can kind of recognize patterns, and you can slowly continue to fill it in. I've kind of cheated a little bit here and skipped over. But again, as you begin to fill in more characters, like we can see the E here, as we were talking about before with the character frequency analysis, we can see that S is used a lot. So we can kind of try and guess and say that maybe E is the character that correlates to S. And when we put that in, you know, we can kind of see this word down here. It's become kind of obvious what that is. So we can fill in a letter for that. And then filling in more letters as we go there, the words start to fill in a lot more. So we can just keep going like that until eventually, slowly, we get our answer without having to brute force, you know, however many combinations are needed in order to get the key. So ciphers like this are what we call symmetric ciphers. So they use the same key to both encrypt and decrypt. Now, this isn't the only way to encrypt messages. And can anyone think why maybe we wouldn't want to do things this way all of the time? Like, why is it a problem sometimes that we're using the same key to encrypt and decrypt? Can anyone think?
Oh, sorry.
Yeah?
Because that like concern that it might get tampered with, like on the way to the.
Yeah.
Customers receiving the message.
That's a really good answer. Yeah, that's a really good point. So you can't really, there's no way to prevent tampering with this system. There's also maybe one other thing that might be a major issue with this. If we think back to like the 4 qualities.
If it's symmetric, then if 2 people have the key, which presumably send messages, you can't verify that it came from one person.
Yeah, exactly, yeah. So everyone's got the same key. So, like, you know, you can't really verify who it's come from. There's no non-repudiation, right? All you know about a message that's been encrypted with this key is that it's been encrypted by someone with the key, which is presumably going to be at least 2 people. So it's not, you know, it's not that useful for that. So yeah, those 2 main things are what we don't really get. We don't get the anti-tampering, and we don't get the sort of authentication and non-repudiation qualities. So what we can do, and we've sort of got the cryptographic primitives here. So there are essentially 3 different cryptographic primitives. You've got the unkeyed, the symmetric, and the asymmetric. So the symmetric is what we just looked at, and the asymmetric is a form of encryption where you can use 2 keys. So essentially what you'll have is you'll have a public key and a private key. So one person will have the public key, one person will have the private key. And the way this works is the sender will use, in this case the sender is using the public key to encrypt their message, and then once that message is encrypted with the public key, the public key can't be used to decrypt that message. In order to decrypt the message, you've got to use this different key here, which is the private key. So you've kind of got this neat little system where you can have two different keys for encrypting and decrypting. And it works both ways as well. So the person with the private key can also encrypt a message using the private key, which can then be decrypted with the public key. So whatever you do, like whether you do a decryption operation or an encryption operation, it can be reversed by the opposite key, but it can't be reversed by the key that you used. So there's kind of some neat little maths around it. I don't really understand it. I don't really like maths that much. I don't think anyone does, really. But yeah, there is a video up on YouTube by the famous Eddie Wu who explains how this all works. And it's definitely not like, it's not massively complicated either. Like it's very much, if it's within the realm of my understanding, I assume you all could probably get it pretty easily. So yeah, again, this is the same kind of idea, a little more explicit this time. So Bob uses, so Bob will give his public key to Alice. Alice can then use that public key to encrypt the message, and then Bob can then use his private key to decrypt the message that Alice has sent him. So the great thing about that is, yeah, essentially Alice isn't going to be able to decrypt messages that are sent to Bob, right? All the messages that get sent to Bob, only Bob can decrypt because only he has these, correlated private key. So what's this useful for in the real world? So a big thing is like anti-tampering. So we use it a lot for e-signatures, right? Can anyone kind of think how maybe, how we could use this to verify a person has sent a message? How we could use this system to kind of authenticate people, enforce non-repudiation, that sort of thing. What technique do you think we could use? Thinking about like if one person has access to their private key and they send out a message, does anyone have any ideas?
If the server sends hey, send me back say hello world encrypted, and then I'll decrypt your public key. If I don't say that, it's not you.
Yeah, exactly. Yeah, exactly. Like essentially, because unlike with the symmetric encryption where everyone involved has that key, in this case we're kind of assuming that only Bob has access to his private key, right? Which means we can send a challenge to him, like as you said, hello world, get him to encrypt it, send it back, decrypt it with what we know to be his public key, and that allows us to verify, at the very least, that the person we're talking to has access to Bob's public key, who we're hoping is Bob for the cases of this exercise. So we use this a lot in web server security. So you might see like the padlock icon at the top of your browser. Your browser, each website you go on with that sort of padlock has a certificate which contains that website's public key. It's all pretty in-depth how that works, but essentially each website has its own private key that's private to it, and the way that sort of communications between you and websites are encrypted is you'll be given its public key, you'll encrypt, sort of a challenge type thing, you'll send it to the server, and then you and the server can use that public private key encryption in order to establish a symmetric key. Yep?
I just got so lost in the earlier slide.
Yeah.
When you decrypt with the public key or the private key?
You can do both. So if you encrypt with the public key, you have to decrypt with the private key.
Right.
If you encrypt with the private key, you decrypt with the public key.
Okay, so you do both with either.
Yep, exactly, yeah. And it's also used a lot for email encryption. For reasons we discussed before, right? With emails, you often want to have that non-repudiation authentication property. You want to be able to tell that the person who's sending the email is the person you think they are. So you'll often do the similar sort of e-signature thing with emails. And cryptocurrency transactions, where it's used a lot as well. And here we have relevant cryptocurrency meme that I definitely understand because I'm well versed in the realm of cryptocurrency. But yeah, cryptocurrency and cryptography are closely related, unsurprisingly. All right, but what about situations where you can encrypt something with no keys? Is that possible? Why would we want to do that? Can anyone, and it's not immediately obvious, but can anyone think of why we might want to be able to encrypt data without any sort of key? Or what kind of application would that have? What would that even look like?
If if you wanted to like verify message integrity, so you have like, here's the message, you say, here's the encrypted, one-way encrypted version.
Yeah.
When you receive it, do the same thing. If it's not the same, your message has been tampered with.
Yeah, exactly, yeah. So the big thing that this enforces is like integrity. We want to be able to check that data hasn't been tampered with during transit, basically. So let's talk about smoothies. I can see Abram was very excited for this analogy over here. But yeah, I think it works very well. Like, it's a good way to think about it. A hashing algorithm, which is essentially an algorithm that can encrypt a piece of data with no key, is a bit like a blender, right? It takes an input, in this case our ingredients, it sort of blends them in order to produce a hash, which in the case of this analogy would be like a cryptographic smoothie, basically. So, you know, it's a fairly simple process. You've got like your ingredients, they go through your blender/hashing algorithm, and they produce your smoothie/hash. So the general idea here is, you know, just like you can't unblend a smoothie into its constituent ingredients, you can't unhash a hash to figure out what input was used. So that's the general idea. Like you can encrypt it one way, but you can't encrypt it the other. So you can take a file, you can run it through your hashing algorithm, and once you've got that hash, there's no way to take that hash and then turn it back into the file. You have to have the file first before you can produce that hash. It'll become a bit clearer as we move on. So there are some key qualities we want our hashing algorithms to have. So we want them to be fast. Oftentimes we're using this kind of hashing algorithm to verify the integrity of files, often very large files. So we want the ability to process them very quickly. So again, no one wants to wait for a smoothie. We want it to be consistent. So we want to be able to use the exact same ingredients every time, and it should make the exact same smoothie. So in the same way, like, we want to be able to know that if we put the same file or the same piece of data into our hashing algorithm, it always produces the exact same hash. And we want it to be unpredictable. So surprises are fun. We don't want to know what kind of smoothie we'll get. So we want it to be unpredictable. We don't want there to be any way in which we can possibly know, like, what the original file was that we've hashed based off of the hash. There should be no way to figure that out. And again, it needs to be quite random. So even if the file changes by just a tiny bit, we want the hash to be completely different. We don't even want to be able to tell if the file was similar. Like, we don't want to take two hashes, see that they're fairly similar, and from that be able to tell that the two files are fairly similar. They need to be completely different, so there's just no way we can analyze it to return to the original piece of data. So what's this actually used for in practice? So oftentimes, you know, when you sign up for a website, the website shouldn't actually have your password in their databases. Some of them do, but they shouldn't. Instead, they should be storing a hash of your password. So this means if the database is leaked, hackers will only have access to that unblendable smoothie, or the hash in this case. So, if the website doesn't actually know your password, how will we be able to figure out if a user has entered the correct password when they try to sign in? Yep.
You hash it and see if it's the same as the stored hash.
Yeah, exactly, yeah. So you can just rehash it, check it against the hash you've got, and you can tell that they've entered the correct password without actually needing to check the password, basically. That's the next. So, before I go on to that, can anyone think maybe just using that strategy of hashing the password, is there any way in which perhaps, like, because ideally we don't want hashes to be reversible, but obviously there are a lot of passwords, a lot of phrases that might get used very commonly. So can anyone think what an issue with that might be? Like, even if you've got this database of hashes, it doesn't have the passwords in it, is there still a way to figure out what the password is?
If you know the hashing algorithm, then you can like try a bunch of common things.
Yeah, exactly, yeah. So basically there's a lot of common phrases like, you know, password 123, what was the classic one? Oh, I can't forget now, but yeah. I forget, like, what was it, like Hunter 2 was like the RuneScape one, yeah. But yeah, essentially, like, a lot of known common passwords exist, and a lot of their, like, associated hashes are already pre-computed and known. So you can go online and you can sort of yeah, you can kind of, people have generated what we call rainbow tables, which is essentially a lot of known phrases that have already been hashed. So you don't have to do the hashing on your own computer. All you have to do is put the phrase in, it'll look it up in its massive database, and it'll tell you like what the associated, what you do is you put the hash in, and it'd look up the hash in its database, and it'd tell you the associated password without any computation needed, basically. Can anyone think of how we might be able to get around this? Yep.
Add something to the end of the password before you hash it that's unique to your service.
Yeah, exactly, yeah. So since we had that quality of our hashes being really random, right, even a small amount of data completely changes the hash, what we can do is you can just add a bit of data to the end of the password, and suddenly you've got like a completely different hash. So you can't do the thing where you look up the hash in a rainbow table or anything like that. It's now completely different, basically. So yeah, as we said, you've got rainbow tables where you can look up like a collection of hashes. So this practice of putting data at the end of our passwords before we hash them is called peppering. Obviously, because you pepper your smoothies before you have them, as any sane individual would do. So the solution to this problem is to add some pepper to the ingredients of the smoothie. And a pepper is just a random bunch of characters that we add to each password before we put it in the blender. And it's going to be ideally unique for each user. So it should really be as unpredictable as possible. This means people with the same password won't get the same smoothie since they have a different pepper. So that's the main reason we want it to be per user. Because there might be an instance where you might be able to crack one password, but if we just use one pepper value, then if we crack that one password that's used across a lot of different accounts, suddenly we can see that hash is used elsewhere, and we've suddenly got all of their passwords as well, basically. So we want to make sure it's as random as possible. And it renders the rainbow table useless, as we said before. Since you can't just look up the hash, it's just a completely random value. So what does hashing look like? Whoops. What does hashing look like? So this is kind of what it looks like in practice. So you've got the user password there. You add the salt, so the random characters. The salt is stored alongside the hash password. The password with the salt goes into the hashing algorithm, and then you get the hash password plus the salt. So you've got the salt, you've got your hash password. This is generally what a hash looks like. It kind of looks big and complicated, but all it really is just a base 16 number if you've done comp 1521. So it's not too complicated. It's essentially just producing a random number that's a certain number of bits long. And once those are stored together, that's essentially all you need to do. And you've kind of solved this issue of making sure you're not storing passwords directly. So crypto TLDR, in order to send a message, we must ensure that the information in the message is sent such that only the receiver can access its contents. Many forms, you've got your ciphers, you've got your public key encryption, you've got your hashing, and they can all be mixed together in different ways in order to ensure we meet those 4 kind of requirements we were talking about at the beginning. And there we've got an example of osmosis cryptography, which is not something we cover in this workshop, but might be covered in one of our more advanced workshops. And with that, I'll pass it back to Lachlan.
Cool. So I'll flag right at the top that we've got an upcoming binary exploitation workshop coming up later, which will go into this in a little bit more detail, and this is just like an introductory little thing. If I could also get a quick show of hands, if you think you're totally 100% down with binary exploitation. Heads, if you've never done anything at all related to this before, and just nothing if you're maybe new, you've just started your first couple of lessons of comp 1511. So hands, heads, nothing, go.
This is all the way.
Good? Good? Not good? Noob. I'm just getting a lot of confusion. That's fine. I'm going to assume that we know nothing then. What is a binary? What is a binary? That is a correct definition for binary. Yes. Good. Who has used a binary before on a computer? Wow, there is a shockingly low number of hands up at the moment. If you've ever done anything ever on any computer, you've used a binary before. Everyone should have had their hand up, I would hope. So if you've done like your first couple of lessons of Comp 1511, for example, you will have used DCC, yeah? If you're a little bit more familiar with writing in C, you'd have used GCC or something equivalent like Clang. And DCC does a bunch of stuff to prevent novice programmers from accidentally causing huge issues on their computer. And those checks and whatnot are a little bit too tricky for us to exploit today. So we're just going to use GCC instead. So first, let's have a look at what GCC does by default to prevent us from being a little bit too evil. So I'm going to call GCC on bad.c. I'm going to ignore my autofill, which is being annoying there. And GCC is going to give us output, which looks like a.out. Is the size good for everybody, by the way? Yep, sweet. A.out is the binary. That's just what GCC names the binary by default. And if we're not familiar with C, I'll just show us what's in that bad.c file. It's a bunch of code which basically looks like some kind of send in a password authenticator. Very, very simple, right? Very simple. Now what we're going to do is we're going to call that binary, we're going to run this program, and we're going to see what happens. It's prompting us for a password. What's a password we want to try out? Shout something out. Shout out your real password that you actually use.
Password 1.
Password 1, Hunter 2. We'll just use password 1 because I heard that first. What's going to happen? Oh man, that wasn't the password. We've got a bunch of stuff there which you may or may not understand. We're probably going to cover it in the later workshop, so don't worry too much about it. This is just a very brief demo to show us something like if we're going, I'm just going to spam something really long. In this particular case, GCC has been a bit smart and prevented the programmer who made a mistake up there, prevented that issue from being a problem. It's going to tell us it detects something called stack smashing, whatever that is, and authentication declines. Now what we're going to do is we're going to pretend we're a bad programmer, and we're going to disable some of those protections that GCC puts in by default. And let's do that now. We're going to use this flag called no stack protector. And I mean, you can probably guess what that's going to do, considering that before it detected some kind of stack smashing, and now we're disabling the thing that protects against it, right? Let's run that. What do we think is going to happen now? What does someone want me to do? Shout it out. If you actually know what's going to happen, don't shout it out. If you're just kind of like, based on what we've done here, what are we going to try to do?
Spam your keyboard again?
Yeah, basically. We're just going to spam my keyboard again. But in order for me to demonstrate something, I'm not just going to do random characters this time. I'm going to do it just in QWERTY order, because we're going to notice something very interesting. We notice that the user password and the system password looks a bit familiar. Where does that system password come from? Well, the thing that it's telling us is the system password. Shout it out.
The end of the user password.
Right, it's just the end of the user password. Because it turns out that the way the programmer has set up this program is they basically just didn't check the bounds of an array, and they've just let us write data straight into other bits of the program. And that's the thing that we exploited in order to do this. And we'll go into much more information about this in the future. And basically, we're just going to spam a massive amount again. We're going to try and aim to overwrite as much information that's currently in memory as possible until it doesn't tell us that we've declined anymore, and it just tells us we've just overwritten basically a lot of the program in memory with our own random bullshit. And now it's no longer knows how to tell us that we typed in the wrong password, and it just goes, sweet, you typed in the right thing, authenticated. And that's kind of our little intro to what was going on there. So that was a relatively simple example, and once again, we're going to go into the weeds of how that works a little bit more in our later workshops. But the kind of core idea there was that the program was bad, and there was a bug in the code which we were able to exploit and basically get around what the program was trying to do. And of course, it doesn't take too much imagination to figure out what happens when these huge, massive, real-world programs with like billions of interns just madly churning out code, they get bugs as well, and we can do things with those bugs. For example, remote privilege escalation. We might be able to kind of run our own code on remote computers, remote servers, and so on. The demo we just looked at was what's called a buffer overflow, where once again we wrote more data than we were supposed to be able to store in the password string, and we just overwrote extra data in the program. You can have a quick read of that or watch the recording which we're doing and freeze the slide or something. If you've done Comp 1521, there's a little bit of information there for you. Cool, so in real life, some examples of buffer overflows. The jailbreaking, which most people have probably heard of. Jailbreaking involves this exploit. A lot of modern malware tries to control bits of memory of your computer which it's not supposed to, and a buffer overflow can help with that. Let's look at another type of overflow, another kind of issue that can happen in our binary. Who's familiar with the int data type or something like it? Yeah? Yeah? It's one of the first things we will learn to use in C, and it basically represents a number, is what we're told. Right? Fair enough? Some kind of integer, some whole number. We've all encountered negative integers as well in C or whatever. Yeah? So integers in C can store values between that and that, slightly dependent on implementation. But on most, like, all the systems that we use in the labs at UNSW, for example, I'm pretty sure that is accurate for. And that is a huge range of values, but we can do something sneaky with that. Time for another demo. We're going to obviously look at what int.c does here. I'm going to show us what's inside int.c as well after, actually. So first of all, I'm going to run this program. All it does is it starts off with an integer which is pretty damn big, and it just keeps adding 1 to it and printing out what we've got. So I start off with I being a pretty big number. I'm adding 1 to it. It's a really big number. I add 1 to it again, and hold on, what's going on there? It's gone into a negative number. That's pretty weird. That shouldn't happen. In real life, when I add 1 to a really big number, it doesn't become a really small number. Something wrong has happened, right? I'm going to show us what's inside int.c for now, and I'm getting issues with that, so we're just going to look at it like this. What's going on here, if you don't know C, that's not an issue. We're starting off with a really big number. That's what int max is. We're going to add 1 to it. We're going to add 1 to it again, and that's what the code for what we just saw was. We're going to go back to this. So why did we get a negative number? So numbers on computers, to simplify it, live on a wheel. So first of all, I want you to look at the inside of the wheel, so where we've got the binary numbers. We'll notice we go from 000, 001, blah, 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 as we expect, up to 0111. Now the next binary number is what? 1000, right? And it continues as we'd expect. However, because integers need to store both positive and negative data, what we do is everything on that left-hand side of the wheel, the computer actually interprets that as being a negative number rather than a really big positive number. And an interesting property is if you look at the left-hand side and the right-hand side and add them together, you'll actually always get 1111. And that's a pretty cool property we'll call one's complement. We'll look at that a little bit later. But the basic idea of that is that what is a really big binary number is actually interpreted as a negative number. And that's what happened there. So we got to a really big number. In this case, this is a simpler case, but it would be like +7. Then we tried to add 1, and then we went all the way back to -8, which is the smallest number in this system. And then now just imagine that on the scale of the huge numbers that we were looking at for our systems. So a famous example of an integer over underflow error in the wild involves the game Civilization. And in this game, each leader gets an aggression level between 0 and 255. Does anyone want to shout out why 255?
8 bits.
Yeah, too easy. Same as the Steg example from before. When a leader in this game adopts democracy, their aggression drops by 2. The issue is that Gandhi starts off with an aggression of 1, right? And if Gandhi adopts democracy, he should go to -1 for aggression. But this game had an underflow error, which is similar to the wheel from before, just in the other direction now. So instead of going to -1, he maxed out at 255 aggression, which results in him attacking us with nuclear weapons, which is not great. Yeah, so that's a little bit about binary exploitation. Once again, please come along to our workshop if you're interested in doing some of that fun stuff, and I'll hand over to Cyrus for the last section on the web.
All right. So the web. So what is the web? You know them, you love them. Websites, right? For a lot of companies, they're kind of like the one thing they have exposed to the internet. So most organizations will have a website. That website will often be the only internet-facing service that organization will have. Or it should, in a lot of cases, be the only service internet-facing that an organization has. As a result, they tend to be kind of a prime target for dodgy hackers, like our friend over here. Oh, I did. I thank Lachlan for his contribution to the slideshow. It's kind of like subliminal messaging. You kind of like. Anyway, what can you learn from a website? So we got like our website here, right? It's a good website, pretty solid, well made. Can anyone tell me, like, if you're just looking at this, you're trying to get information, you're trying to look around, you're trying to figure things out, like, where can you look when you look at a website? What is there to look at? How can you navigate around? Yep. Yeah, so like sort of going to different pages, right? Looking around, seeing what pages are on the web application. Is there anywhere else there might be like hidden information? I don't know if anyone was a bit of a high school hacker and used to, used to alter web pages in some way, yeah?
Inspect element?
Yeah, exactly. Like viewing the source code of the page. So you'll have the way the page is displayed, but it's got a bunch of source code underneath it, which determines like, you know, how it's displayed, what runs, that sort of thing. So there can be stuff hidden in there. There's other slightly less obvious ones, and I wouldn't be surprised if people might not get them, but can anyone think of any other information that might be associated with this site? Like what else could you look up to find stuff? Yeah?
You could do some subpage enumeration.
Yeah, so it's in like kind of the directory side of things? Yeah, so that's a good one. Yeah, you can like get like, and we'll look into this in a second, a big list of words and just check like which ones exist on the web page. Is there anything else? And there's like, yep.
Do a whois lookup.
Yeah, that's a good idea as well. Yeah, just take the domain, do a whois, see what information's there. Yep.
You could look at the Wayback Machine, see what the website looked like before and past.
Yeah, I like that as well. Yeah, that's really good. Any other ideas? So really there's like that. I mean, as we've seen, there's like a lot of stuff you can do. Like just looking at this web page, there's a lot of places you can go for information, a lot of little things you can look at. There's other things, right? There's subdomain enumeration, so you can kind of, we'll look at it in a second, but you can kind of, you know, see if there's any domains under UNSW security that have any sort of like websites or services or anything like that. And yeah, there's just a bunch of stuff you can look at. You know, Showdown, you can look up the IP, so many things. But I guess in order to understand that, the first thing we need to understand is how does the web actually work? Like when you go to a website, what actually happens? Does anyone know, does anyone have a crack at like, you type a URL in the search, in the URL bar, whatever it's called, you hit enter. Does anyone know what actually happens behind the scenes when you do that? Yeah, it's a DNS. So the first thing that'll happen is that URL will get sent out in a DNS query. So the thing with the URL is computers don't really understand URLs. They're not really good for routing traffic around. What the computer actually wants is something called an IP address, which looks something like this here. It'll usually be in this format, unless IPv6, but we won't get into that. And that's the number a computer can attach to like a packet of data, send it out onto the internet, and all the routers can use that number to send that packet to where it needs to be. So that's the first thing we need to determine. So the way that we do that is your browser will send out a query that looks kind of like that. It'll say, what is the IP address associated with google.com? The magical mystical DNS system will say, this is the IP address associated with google.com, and we'll send it back to your browser. Your browser can then use that IP address to access the website itself. So when it comes to actually accessing the website, does anyone, I don't know how I want to put this exactly, but like, does anyone kind of know what your browser does in order to get information from an HTTP server or a website? Like what, it's got to send something out. Does anyone know?
Headers.
Sorry?
It sends headers, like in a request.
Yeah, so that's pretty much it. So what it'll do is it'll create a request and it'll send it to the web server. So websites run on a service called HTTP, so that's Hypertext Transfer Protocol, and there's a bunch of specifications for that. But essentially, HTTP servers accept requests and return responses. And those requests and responses look pretty much like that, exactly like that, actually. So you'll have, your average GET request will have a whole bunch of headers. They do a whole bunch of different things, and the server itself will send back this HTTP response that will have a bunch of headers in it along with the HTML code. Now, looking at this, there's a lot of information here, right? So this is kind of another place you can look, to find information about a website. Can anyone maybe pick out any interesting things, particularly on the response side? If you were thinking, if you're in the mindset you want to kind of find ways to exploit this server, or you want to find information about this server that might help you paint a picture of what, the system in question looks like. Is there anything that you would possibly look at? And I've given you a hard one here because this is literally google.com, which is probably one of the most secured websites on the internet, I hope. But even so, is there any information here that you might find interesting without knowing, what a lot of it is?
The set cookie header has a path that ends with slash, and usually if you have a slash, it implies a Unix system. So the server is running some sort of Unix distribution.
I like that observation. It's not necessarily true, but I do like that mindset of looking for that. What that's doing in that case is it's referring to the scope that the cookie's set for from memory. So it's actually referring to whether the cookie's valid, on the website. But I do like looking for file paths and that sort of thing. That's a very good thing to look for. Yeah?
This is just really dumb.
No?
It says XSS protection 0. So you do some XSS thing and it can't protect against it because it's 0.
That's a good point.
Yeah.
And it's a little embarrassing for me because I now at the moment cannot remember what that header is supposed to be set to in order for it to be secure. Yeah.
Okay, so the XSS protection header was a bit of magic that was instituted a while ago. It's been deprecated now because it could still be exploited essentially, and it made a bunch of people think they were safe when they definitely weren't. So the header's there because I think some browsers still expect it, but it's not a used technology anymore.
You can correct me if I'm wrong, but I believe the functionality that's supposed to have is now kind of covered by, do they have a content security policy here?
Yeah.
But yeah, essentially there's another header which kind of does that stuff now. But yeah, again, I like that observation. Looking for little details like that is good. I think you were going to say something at one point?
I was, but it was just something similar to what somebody suggested.
Yes.
It's line 6 of the second document.
Line
it
6.
says security, so you can change it.
Yeah.
Or whatever.
I like that thought. Yeah, okay, yeah, I see, yeah. No, I definitely like looking for those little sort of key points. Another thing you might look at, and again, there really isn't much here because if there was something here to exploit, it would have been exploited a million times over. But stuff you might look for in other places is you've got that server header there. A lot of websites you'll encounter will just straight up tell you the exact version of Apache or Nginx they're using. On its own, not massively useful information, but when you're trying to form a picture of a system, as you said, whether or not it's running Apache or Nginx can tell you what operating system the system's using and stuff like that, which, you can't exploit that on its own, but if an attacker's, trying to knock on the doors, see what's unlocked, it helps them form a bigger picture and it gives them information that they can possibly use later on. So it does present a marginal but a risk nonetheless. So this is sort of the other part of the HTTP response. So you'll see we've got the response here, that's all the headers. Below that, it'll send you the actual HTML that your browser needs to display. So we can access this by just going into our browser, right-clicking the page, and then hitting View Source. In this case, this is not google.com's source code, in case you were wondering. This is some I prepared earlier. But this kind of highlights the point of, you can find valuable information here as well. Now, a big thing people tend to look for is these things here, which are comments. So I don't see this that often with valuable information. I think in CTFs, often sort of beginner to moderate ones will have information in comments and that sort of thing. But I mean, realistically, like, yeah, developers can leave comments in there. Those comments can have sensitive information. You can get information that way. You can also find out a whole bunch of other stuff, like if they're using JavaScript libraries, these will all be included in there. They'll usually tell you what version they are. And you can usually get a good sense of like how the web page works just based off its HTML code. Whether or not it's kind of like a single page application, whether or not it's using primarily front-end stuff versus back-end and that sort of thing. So what do you actually do if you're faced with a web application and you want to find out as much information as possible? So the first stage of testing a web application should be to figure out what the application itself looks like. So as we saw before, like, you know, we want to find out what's there, because as we saw, there's a lot of stuff, right? There's the HTTP requests, there's the source code, there's all the pages, there's, you know, Wayback Machine stuff, there's like tons of information, and you want to find everything because you want to have as much data as possible, right? So we want to be able to find as many pages as possible, as much content, because having the ability to access that gives us more attack surface, more stuff to kind of, you know, more doors to knock on, more kind of stuff to attack, and that means there's a greater chance you'll find something vulnerable, which means more epic hacker moments for you, basically. And it's kind of like that analogy you had at the start of the fence that's got like the holes on either side, right? Like maybe you're just looking around the web page at a surface level and you don't find anything, but maybe you do some sort of directory brute forcing and who knows, you find a page that's like, you know, what's a good example? A WordPress login that's just like admin, basically, or something non-obvious. So you want to be able to expand that surface as much as possible and you want to find that door that's kind of unlocked. So the main way we do this, or often initially when you're beginning testing a web app, you'll look for subdomains and you'll look for subdirectories. So a subdomain is the thing that goes before the dot. So a subdomain of this domain would be like test.example.com. So, you know, you want to find like all the domains below that domain that the company is using, because those can often host other websites, or they can host other services, or they can host just about anything, really. They can be referring to a completely different server that the company controls, or something like that. And then you can also do subdirectory brute forcing. So that's the stuff that goes after the slash here. So you might notice when you're clicking through a website, you know, you click the home page or the FAQ page or the About Us page, you know, that the word that goes behind that slash will change, indicating you've gone to another page, right? So you know, you want to be able to find as many of those pages as possible.
Yeah, if I could just jump in for a second, just to reiterate, if you saw like a URL somewhere which was like google.example.com, that's not belonging to Google, right? That's belonging to whoever owns example.com. Mm-hmm. Whereas if you see like example.google.com, that actually belongs to Google, not example.com. Does that make sense? So that's just like to try and get you to understand how that subdomain works.
Yeah, that's a good point, right? It goes a bit in depth, but like, essentially you've kind of got the most authoritative subdomain on the right-hand side, and they kind of go down in level of authority. So com, sort of, you have to be registered with com in order to have example, and then example controls whoever has access to the domains below that, so on and so forth. Okay, so we've got an example web app here. It's pretty basic. It just says that. And we want to be able to find if there's anything else on this web app that might be interesting to look at. We want to have a look around. So, you know, I've talked about like, you know, subdirectory brute forcing, subdomain brute forcing, but how do we actually do this in practice? There are a number of ways. There's a number of tools you can use. What you'll have to start with is like a word list, basically. So there's no real easy way to like see what subdirectories or subdomains a website has. There's no kind of registry that lists every subdirectory a website has. You know, there's no functionality that does that. Unless you've got access to the server itself, there's no real easy way to figure that information out. So what you'll have to do is you'll have to guess. And in order to guess, you've got to have a load of different words that you want to use to guess with. So this is an example of an extremely short word list. Excuse me. Usually they'll be a lot longer. Like, I mean, they can be tens of thousands, hundreds of thousands, millions of words long. And they'll often contain things like this. Like, this particular one contains keywords that are very common. So robots.txt, we'll discuss that in a bit, but you know, it's a pretty common page on websites. Sitemap XML is the same. You know, things like login, WP login, FAQ, help store, they're all very common words. And there are places you can go to get big word lists like this. If you search up sec lists on GitHub, it's got a massive repository of like loads of word lists that are often like highly specialized for this sort of thing. What do we do with this word list? Well, what we want to do in this case is we want to use a tool which can access all of these subdirectories really quickly and tell us whether or not there's an actual page at that subdirectory. So we take our word list here, we put it into this tool, and what this tool will do is it takes our URL here, and then it sends a request with the word substituted where it says fuzz, basically. So, for example, it'll send a request, instead of the word fuzz, it'll send robots.txt and sitemap.xml and so on and so forth, a bunch of times until it can actually find, it'll just tell you what response the server gives. So, if a page exists on the server, more often than not, it'll give a 200 response. If the page doesn't exist, it'll often give you a 404 response, but it can also give you a bunch of others. And again, if the page exists, it can also give you like, what is it from me? 403s are the unauthorized ones, I think. Or, yeah, there are a bunch of different responses that can indicate different things. And in the real world, you won't see like 200 responses cleanly for every page that exists on a site, generally speaking. But we can see here we've run this tool, and it's come back to us, and it's told us that WP login,
So why does it give like 200 or 500 like different responses if it does exist?
Yeah, that's a good question. So basically in the HTTP specification, if we go back to our request, so HTTP specifies a bunch of these codes to be sent in responses from web servers. So you can see up here, this one sent back a 200 OK response. So this is kind of a quick way for your browser or whatever tool is kind of accessing the page to determine, like, if there's an error, to determine what that error is, or like if you're not authorized to access the page, to determine that very quickly. So if you just have normal access to a page, you'll get 200. You might have seen you've probably seen 404, that's kind of the famous one. So an HTTP server will return 404 if that page does not exist on the web server, basically. There's also ones like 500, which indicates that the servers had an internal error. I don't know them all off by heart, but there are others that indicate things like it's unauthorized or so on and so forth. And if you look it up on Wikipedia, there's like a whole big list of what all these different codes mean. But it's basically conforming with this specification just to make things easier, like when you're writing programs that interact with HTTP servers, basically. Does that make sense?
Yeah, it makes sense.
Okay. But yeah, that's a good question. So in this case, yeah, it'll tell us all the statuses. It just rips it out of the request or the response that it receives. So yeah, we can see we've found like WP login, sitemap.xml, and robots.txt. Those pages out of the ones we tested here appear to be present on this web application. So now that we've got these pages, what we want to do is we just want to go have a quick look at what's at each of these pages. So, a video makes it hard to see there, but, oh wait, hang on, have I changed the desktop here? I hope not. Alright, we should be right. So yeah, we go to, which one is this? WP login, and we see there's not a whole lot there. It's just another plain text page because I am too lazy and too unskilled at front end to make anything else. Go to the next one, and I hope this works. Yep. Again, we see like another plain text page. And this will often be the case, right? You'll check a whole bunch of pages, and most of them will be supposed to be there. There won't be anything particularly interesting. If you're doing this in the real world, something you might want to note is like input fields, stuff we could potentially exploit, whether there's any interesting information there, and stuff like that. And as we see on the next slide, if we go to robots.txt though, we can see it's got this entry here. It's user agent wildcard disallow free shells are us. So what the robots.txt file does is it kind of tells Google and other web crawlers like that not to index these pages. So if you own a website and you don't want certain pages to show up on your search engine, you can put them in here and they won't show up. Can anyone kind of identify the problem with doing this in order to hide web pages?
Everything that you wanted to hide is now like easily accessible.
Yeah, exactly. Yeah, precisely. Like, so a lot of, well, I don't want to say a lot of, but some web developers think that this is a method by which to obscure pages and will, obviously put in a bunch of like pages that they don't want people to be able to access in, you know, substituting for proper like access controls and things like that. So often you can find interesting parts in this robots.txt file, which allow you to further, you know, expand your attack surface basically. So we can see we found this free shells are us. So if we go to that page, we'll find this nice little login here. And does anyone recognize what this is a login for? WordPress, yeah. So again, like just on its own here, that's useful information, right? Because if we see this login page, we know that this web app's running WordPress, and that in and of itself can be quite useful because there's a lot of exploits and things like that that are specific to WordPress that you might be able to use, or techniques or tools that, you know, you can further use to expand your attack surface. And can anyone think, like, beyond just being able to access information, like what could you do here? Like as an attacker, if you're a, you know, a hacker person trying to break in, what would your thoughts be when you get to this login screen?
Look up WordPress default passwords.
That's a very good idea, yeah. Look up like the default configuration passwords. Is there something else you might try if you couldn't find any default creds?
Try the website owner's email and
Yeah.
just random passwords that...
Yeah. Yeah, it's a good point. Like, now that you have access to this login form, depending on how WordPress has been configured, you could feasibly do a similar thing to what we did with the subdirectories. You could just get that tool, set it so that it has like a bunch of usernames and a bunch of passwords, and then just set it loose on that form and see whether or not you're able to find any valid username and password combinations in order to log in. So, like, there's a lot of stuff you can do with this, and it kind of goes to show that, particularly with web security, like, it can be extremely complex because web apps in and of themselves are just insanely complex. There's a lot of moving parts. There's a lot of different things built on top of each other, and I think it very much conforms with that sort of analogy we had at the beginning of like the fence with the space on either side, right? You're just constantly looking for that one sort of weak point, basically. And if the web app is big enough, that it will almost always exist in some capacity. So what now? So we won't go too in depth here today, but a few things to read on further if you're interested. Once you've done a lot of this enumeration, once you've kind of figured out where all the web pages are, where all the subdomains are, what's kind of going on with the web application, you can move on to looking for things like cross-site scripting, which allows you to kind of insert HTML code into the web page to do stuff. You can do SQL injection if you find a database, which lets you manipulate databases that the website is using. There's IDOR, you can inject commands and that sort of thing, template injection, and there's just 1,000,001 other kinds of attacks. Some of them are general, some of them are extremely specific to particular technology stacks or particular content management systems and stuff like that. It's a pretty big space and it's quite varied, and it's definitely longer than we can cover today. Or you can come to SecSoc's fantastic, amazing web app testing workshop, which is definitely coming soon. On a completely unrelated note, if anyone here is interested in presenting a web app testing workshop, feel free to come to me at the end and make yourself known. So with that, I guess we'll just kind of move on to what comes next. So that's kind of the end of the main technical content of today's workshop. But hopefully, or almost certainly, this will not be the last workshop we run this year. In fact, I hope it's the first of many. So there are a few things we'd like you guys to be aware of that are coming up this year. So I don't know if many of you were around last year, but Scones is our kind of student-held security conference. There's some debate about how the name is pronounced, I think. But yeah, it basically has beginner-oriented security talks, real-world security companies, our sponsors coming in and doing talks, lots of merch and good vibes, and stay tuned for updates by joining the Discord. I think there's a link on the next slide, but definitely try and come to that. We're also hoping for more workshops this year. We've already got one about to be booked in, if I can get around to doing that tonight, and hopefully we'll do at least 2 or 3 more this term. CTFs, hopefully some of you participated in our beginner CTF at the beginning of the year. Nice, that's where you got the shirt. Yeah, respect. You can have like hot bling like that if you join our CTFs, basically. That's what our ARC money goes towards. But yeah, our CTF team does a very good job with that, and hopefully, I don't know if there are any others planned for this term, but hopefully there will be more next term. In fact, we're hoping to run a few next term. And it wouldn't be a proper education workshop without me shilling the education subcommittee. So if you're interested in potentially helping to organise these workshops, please join our subcommittee. Please, Lachlan and I haven't slept in weeks. So we're hoping to get some subcommittee people to come in and help us out. But I think is there anything else we've got to add there?
Sounds good.
Sweet, yeah. Oh,
Two
yes.
things. One, application for subcom should be opening sometime next week, so keep an eye out for that. Second thing, if you haven't completed the attendance sheet, please do so.
There's a faster way to do this.
How do you do it? How do you do
It's
it?
how we get our money. So, please make sure you do that.
Yeah, if anyone hasn't, we'll get the QR code up in a second. Please fill out.
Oh, wait, maybe this isn't faster. That'd be sad, wouldn't it?
Now you're revealing all our secrets out.
How do I skip to the start? Surely I think it's at the start. Surely.
Start from the beginning, yeah.
Surely there's a way.
Can you please? Nice.
I think that was technically faster.
There we go. If you haven't filled it out yet, please do it. I put a QR code up. And thank you all for coming.
I think about 12.